All right, hopefully you've had time to work on this handout to compare flow around the boundary compared to the total flow inside, using these rules to add up the flow inside any particular triangle in this diagram. Here's what I got when I worked out all of the circulations inside for each triangle. And when I add things up around the inside, I get a total flow of 35, a circulation of 35. And when I add things up only around the boundary, I also get a flow of 35. I hope as you were doing all of these calculations, you noticed that for every edge on the interior, for all of these interior edges, you touched each one twice. Once going, right, because each edge is adjacent to two triangles. So, for example, for this edge with a flow of 1 going to the right, it contributes a +1 to the triangle above it, but for the triangle below it, it contributes a -1 because we're traversing that edge in the opposite way. And that actually happens for every edge, not just this one. So when you add up the total circulation for all of the triangles individually, all of the interior edges, they count once positive and once negative, so they cancel. All of the interior edges cancel, and you're left only with the boundary edges. But if you look at all of the boundary edges for all of these triangles that traverse one of the boundary edges, all of the boundary edges get traversed overall going counterclockwise like this, which is the way that we traversed them when we computed this boundary just around the edge. So it's not a coincidence that these two came out to be the same, apparently, right? So there's nothing actually special about the particular numbers in this diagram. They could have been anything, and still these two would have come out to be the same. So that's kind of interesting. The way that we've added things up, the total circulation around, or the circulation around the boundary, is always going to be equal to the total local circulation added up on the interior of this region. All right, so when you worked out flux across the boundary for this different region, something very similar happened. The total flux looking only at the boundary of this region turned out to be 6. But if you add the flux for all of the individual, if you calculate the flux for all of the individual triangles in the interior and then add up all of those totals, you also get 6. And hopefully, as you were doing this calculation, you noticed that much like the last example, even though this is flux and not circulation, still each interior edge, like this 4, gets counted twice. Once for each triangle that it's adjacent to, but for those two triangles, the 4 contributes with opposite sign because this 4 is flowing into one of the triangles, so it will count as negative for that one, but it's flowing out of the other triangle, so it will count positive for that one. So all of the interior edges will cancel, and you'll only be left with the contributions for the boundary edges, because, of course, those don't have another triangle on the other side to cancel with. So again, it's not a coincidence that these turned out to both be the same. That would actually always happen. So it looks like the total divergence, or the total flux across the boundary, is equal to the flux across the boundary is equal to the total flux added up over the interior of this region. So that gives us sort of a sensible guess for how flow and flux should work, how circulation and flux should work for regions in general. For circulation, it looks like the circulation around the boundary should be equal to the total circulation over the interior. And for flux, it seems like the total flux through the boundary should be equal to the total flux over the interior. But let's think about in this handout, this situation is, I guess you could describe this as being discrete, because we have these separated triangles that are have well-defined boundaries between them. But in a vector calculus context, we're dealing with continuous things and not discrete things. So let's reinterpret what each of these quantities would be if we express them in terms of vector calculus. So for circulation around a boundary, well, we know exactly what that ought to be. Circulation around a boundary, that is the integral over the boundary curve of f dot dr. Right? So what would be a way to measure total circulation over the interior? Well, to total something up over a region, that should be a double integral. But what should, so dA, but what should we be adding up? So what is sort of the local version for vector fields? What is the local version of circulation? If we have a vector field f, what quantity about f tells you how much the vector field is circulating around any infinitely tiny little patch? Well, that's what curl is for. That's how we invented curl. So it seems like we should put curl here. And, our experience with the discrete example would lead us to guess that maybe these two things are related. And of course, the most simple relationship would be if they're actually equal to each other. So we actually don't, this isn't a proof by any means. We're guessing at this point. But wouldn't it be nice if these two ways of measuring circulation actually gave us the same thing? All right, well, what would the corresponding thing for flux be? Again, we already have a definite way of calculating the flux through the boundary curve. So that would be the line integral over the boundary curve of, it would be our flux integral, which is, remember, f dot n ds is how we expressed that one. So what would the total flux over the interior look like? Well, again, integrating over an interior, that would be a double integral dA. So integral over the interior region. But what thing about a vector field tells you how much it is spreading away from a given point? Well, that's divergence. So our experience, and wouldn't it, so we have these two ways of measuring total flux with vector fields, and wouldn't it be nice if these were related to each other in some way? Our experience with the discrete case, again, leads us to guess that, hey, maybe these are actually equal to each other. All right, so we have these two guesses about vector fields, but right, these are guesses. We don't really have any firm reason to believe that these are actually true. One way to build up your willingness to try to prove something difficult is to check a particular example and to see if it's true for the example. So before we dive into trying to prove these things, let's see if it's actually true for an example. So let's look at the circulation of this vector field, x plus y, comma y minus 2x, around this square. And we'll measure this circulation in two ways. We'll measure it around the boundary, and we'll also measure it over the interior, and we'll just see if those things turn out to be equal. Okay, so this square, unfortunately, this square has four sides, right? So we're going to have to compute, to go around this square counterclockwise, we have to go like this. And so we're going to have to do four line integrals to find the circulation around the boundary, but none of them is very, very difficult. So let's name these curves C1, C2, C3, C4. Okay, and let's calculate these line integrals. So here we're going to go around the boundary. Oh, I can't spell today. Boundary. So for C1, our parametrization for C1 is just going to be, looks like t comma 0, and t is going to go from 0 to 1. So the derivative of that is 1, 0, and so our integral is from 0 to 1. Our vector field is t plus 0, comma 0 minus 2t. We're dotting that with r prime, which is 1 comma 0 dt. So we're integrating from 0 to 1 t dt. And so that's integral of 1/2 t squared from 1/2 t squared from 0 to 1. That's a half. Okay, now let's do C2. C2 is going up the right-hand side, so the x-coordinate there is 1, the y-coordinate is t, and t is going to be going from 0 to 1 again. So integral from 0 to 1, x is 1 plus y is t, comma, y is t minus 2 times 1. Okay, and this time r prime is 0, comma 1. So when we evaluate this, or when we do the dot product, we get just t minus 2 dt. So when we integrate that, we get 1/2 t squared minus 2t from 0 to 1. So that's going to be 1/2 minus 2, that's minus 3/2. Okay, we're getting there, halfway done. Now across the top, y is always 1. And we can use just t as long as t goes from 1 to 0. Because remember, we have to traverse this from the upper right-hand corner of the square across leftwards. So, so we have to start at t equals 1 and go to t equals 0. So that's going to give us integral from 1 to 0 of x plus y, so t plus 1, comma, y, which is 1, minus 2x, which is t, and then dotted with r prime, which is 1, comma 0, dt. So we're integrating from 1 to 0, t plus 1 dt. So this is going to give us 1/2 t squared plus t from 1 to 0. And that's going to give us 0 when we plug in the top bound. When we plug in the bottom bound, we're going to get 3/2. But remember, that picks up a negative because we're plugging in the bottom bound. So minus 3/2. Okay, now finally, oh, that was C3. Finally, we have to do C4, which is coming down the left-hand side of the square. So the y-coordinates there are always 0. The x-coordinate we can take to be t as long as t goes from 1 to 0, so that we're coming down the left-hand side instead of going up the left-hand side. So integral from 1 to 0 of, so it was x plus y, so x plus 0, comma, y minus 2x, so that's minus 2t, dotted with r prime, which is 1, comma 0, dt. And so doing the dot product, we get integral from 1 to 0 of t dt, and that's going to give us, right, 1/2 t squared from 1 to 0, and that's going to give us minus 1/2. And minus 1/2 because the non-zero term comes from the bottom bound. So now adding up all of these, we get, looks like, so 1/2 minus 3/2 minus 3/2 minus 1/2, that's going to give us minus 3. So total minus 3. Okay. Now remember, the other way we thought we might be able to measure circulation is to do the double integral over the region of the curl of f dA. So fortunately, this region is a square, so we can go from 0 to 1 in the x direction and 0 to 1 in the y direction. Now we just need to calculate the curl of this vector field. So partial derivative of that, partial n partial x. Right, so this first bit, we need partial n partial x minus partial m partial y. So that's going to give us minus 2 minus 1. So the double integral, or the integral over this unit square of minus 3 dy dx, but that's going to be minus 3. And look, it is the same, right? We got minus 3 integrating the curl over the interior of the square, and we also got minus 3 calculating the circulation of the vector field around the boundary of the square. So this gives us maybe a little confidence that these guesses that we made, maybe they're actually true. So it seems like it would be worth it to spend the time to try to actually prove this. So let's do that next.